The other major upheaval was the birth of quantum mechanics. By contrast, the implications of quantum physics for cosmology are still far from understood. Okay, so some people like Stephen Hawking actually have used quantum mechanics in a more bigger sense, as in to integrate certain things about black holes, which were traditionally or historically a classical object, if you will. They came from a general relativity or a classical prediction, but he incorporated quantum into black holes, right? So not everybody completely ignores that there is general relativity as well as quantum mechanics, I would say, but to a large extent, the classical physicists don't always consider quantum, and the quantum physicists don't always consider classical. Okay. So, in the world, according to quantum theory, every entity has a dual nature. In classical physics, two distinct concepts were used to describe distinct natural phenomena, waves and particles. Quantum physics tells us that these concepts do not apply separately to the microscopic world. Things that we previously imagined to be particles can sometimes behave like waves. Phenomena that we previously thought of as waves can sometimes behave like particles. Light behaves like a wave. So light actually has both wave and particle duality. By the way, if you, one little trick to remember which one light is going to be more like, if you're considering the very short wavelengths of light, for example, gamma rays, then you have more of a particle nature of light. Gamma rays are almost like particle light, as in photons. Being hit with gamma rays is like being hit with particles. Okay, very short wavelength, very high frequency, almost like a particle, right? And it does have particle nature. If you want to consider light as a wave, then think of it as the bigger wavelengths. If you have longer wavelength, light, for example, radio waves, then it is more like a wave and less like a particle, right? So light, for example, has wave and particle duality, but how it shows up or how it manifests in the physical is what I just told you, which is that if you have longer wavelength light, it's going to manifest physically more like a wave. If you have shorter wavelength light, it's going to manifest physically as more like a particle. Okay? So one can produce interference and diffraction effects using prisms and lenses with light. Moreover, Maxwell had shown that light was actually described mathematically by an equation called the wave equation. The wave nature of light is therefore predicted by this theory. So pretty much Maxwell's equations or the E&M, those are all considered classical theories, and it treats light like a wave, okay? On the other hand, Max Planck's work, so Max Planck is a contributor to quantum mechanics. So that work on the radiation emitted by hot bodies had also shown that light could also behave as if it came in discrete packets, which he called quanta. So there we go, light having a wave nature as well as a quantum or particle nature.